Now that we've talked about the main tools and techniques for the course, we're actually going to spend the rest of the class talking about specific systems that are relatively important. We're going to start off with the first one, which is by far the most important system, and that is a harmonic system, or a simple harmonic system. To do so, though, we have to talk about elasticity. Now, the idea behind elasticity is for a variety of different systems, they can exist in a state known as equilibrium, which basically means they're at some kind of position or orientation where they're likely to stay. Equilibrium is a difficult word to spell, so hopefully that's right. Now, this equilibrium can be quite varied. So because this is a class dealing with physical things, we're going to talk about this in a physics context. But I'm also going to show you some examples where this equilibrium idea and the exact same mathematics that we're going to learn throughout this entire section can actually be used in other contexts. They're pretty much applied in the exact same way. So here we have two objects. They could be anything. They could be two atoms with a bond between them. They could be, two populations of codependent organisms. It really doesn't make a difference. But we're going to look at where they are. So each one has a position, and this black line in the middle of them represents how far they are apart at equilibrium. Now, equilibrium means that if they want to be r distance apart, they're going to want to stay there. So in order to examine equilibrium as a constant or as a concept, what we need to do is not only look at where they are, but ask ourselves what happens if we were to displace them from equilibrium. So let's say we were to take one of them and we were to move them further apart. So we were to push them further apart than their natural configuration that they want to be at. Well, generally speaking, if this equilibrium is real, what you'll see is you will see them be pushed back together. And this pushing back together can be related to a concept that we've talked about before, known as a force. And this is, of course, a vector pulling them together. Now, we can also compare this force to how far we pulled them apart. In other words, since we've changed their relative positions to one another, how far we pulled them apart is a displacement. And specifically, I'm going to refer to this as a displacement from equilibrium. Now, what you'll notice about these two systems is if they are in an equilibrium system, the force and the displacement are actually opposite in direction to one another. The idea behind this is if our system wants to be at equilibrium, any change from equilibrium will be counteracted by something that will try to pull it back together. Now, for mechanical systems, the simplest approximation for this system is that this force is proportional to this displacement from equilibrium. Now, mathematically speaking, we can represent this with a simple equation in which our force is equal to negative some proportionality constant times the displacement from equilibrium. So the simplest approximation here is known as Hooke's model of elasticity, or Hooke's spring model, with the k there, the proportionality constant being referred to as the spring constant. We can also take this a step further and do some mathematics to find the potential energy associated with displacements from equilibrium in these types of systems, and that's this U spring, or potential due to a displacement from equilibrium in a simple spring-like system. Now, this here is a purely physical model, and it represents both, or the majority of physical models that we deal with. So if you take any physical object and you push down on it, it does compress slightly, and that creates a force that tries to restore its equilibrium, so long as your object has an equilibrium state it wants to be in. Now, there are some systems that don't really have an equilibrium state, but they're very, very rare. Even something like air, which you typically can't view yourself as pushing on, does have an equilibrium configuration. If you blow air out of a room, it's going to try to get back into the room due to entropy. So again, it can follow a model of this type.